something called a reversed Carnot engine. In this case, I have W net going in, I have Q in at TC. So now, in this reverse Carnot engine, the heat in is not at a high temperature, the heat in is at a low temperature. I'm adding work to it, and I'm getting Q out at TH. So if I look at this Q out, the Q out, where did that energy come from? Came from Q in plus W net. So this represents Q out, and I have W net and Q in. And what we're going to see is that we're able to leverage, we're able to take energy at a low energy value, add to it a little bit of energy at a very high energy value, and get energy Q out at the level we want. And so let's look at what this diagram looks like if I have the reverse Carnot engine. Reverse means it's going to go in the opposite direction. So if I look at a PV diagram, I'll start at state 1, but now we're going to have a reversible adiabatic expansion to state 2. We're expanding from 2 to 3, and we're having Qn at Tc. So heat's going in at the low temperature, just as we see here, but now we see where it occurs in the cycle itself. We then have reversible adiabatic compression from 3 to 4, and then from 4 to 1, we have Q out at TH. And if I look at this, we're going to have another expression. We don't use efficiency for reverse Carnot engines. We use something called coefficient of performance, and we'll see why. We end up having a number greater than 1. So if I use philosophically the definition of desired effect over cost of effect, so I have this, and now what I want to do is I want to have cooling. So the desired effect is Qn, and the cost of the effect is W net. And we call this coefficient of performance, COPC, C for cooling, coefficient of performance. So I have the coefficient of performance. We look at it this way, and the analysis is similar to what we did for the analysis is similar. What we come up with, though, is a different expression. So the COPC is equal to TC over TH minus TC, and this is equal to Qn over W net. So this is where the desired effect is cooling. And let's just think about what that might look like. So let's say that we have a house. So here's the house, and we want it at 24 degrees C. And let's say that it's 32 degrees C outside. So it's hot outside, and what's going to happen is we know the heat's going to go in here from the outside. So this is like, thank you very much, why am I taking this course? So I have heat going in, so I'm going to have my reverse Carnot engine here. And what it has to do is remove heat. I need the heat coming out at 24 degrees C and going in there. So this is my Q in at 24. Then I'm going to add work to it, W net, and I'll have Q out at 32. We're not assuming that there's any temperature difference, but basically another condition such as the cooling load on a refrigerator, the cooling load for air conditioning on a house, those are the things that determine the QN. And basically if I wasn't removing that amount of heat, the house would heat up, would rise in temperature. And so it's this condition, a refrigerator, a house, or something like that, that establishes the need for our having cooling. I'm sure you felt, there are heat pumps, but you may have felt with a refrigerator, which you know keeps things cool, and the same idea occurs there, except the refrigerator I want at a lower temperature, heat leaks in from the outside, vegetables can decay, there's all sorts of things that cause the temperature to rise, so why I have to remove heat, and it goes into it's not a reverse Carnot cycle, but it goes into a vapor compression system. But the concept is the same thing. And what happens if you felt around the refrigerator, there's warm air that comes out somewhere, on the bottom, on the top, somewhere. But if I wanted to stay warm, what if this were the winter time? What if this were the winter line? Let's change this to winter time. Now I'm going to have the same house, and I want it at 24 degrees C, and outside it's 0 degrees C. Well, I might as well make it minus 4 degrees C because I'm going to do an example like that. So what's happening now is that heat's leaving, right? So it's going to get cold inside, so I need a reverse Carnot engine. I'm going to put heat in, and now I want the heat out at 24 degrees C to keep me warm. And where am I getting this? I'm having Q in at minus 4 degrees C come in to help it. So now the Q out is the Q in plus the W net. And this is the concept that heat pumps work on. But there's a different coefficient of performance because the desired effect is different. So there's a coefficient of performance for heating. Being ever so low. So here the desired effect is Q out, and it's W net. Notice that it's referenced to the reverse Carnot engine. So the desired effect isn't about the house. The house decides what's needed, establishes the load. We're referencing this, and so we call this a coefficient of performance for heating, H for heat. So in this case, the COPH is going to be TH over TH minus TC. And so what we can do is now apply this, and there's a problem in the text, problem number 715, which I'll do, and we'll see how to establish this. So let's look at problem 715. So if I look at a problem 715, I have a house. I want to keep it at 24 degrees C. I have a reverse Carnot engine. And T summer is 32 degrees C. T winter is minus 4 degrees C. So we have this condition. Now the house has insulation, and basically heat is lost or gained basically on the insulation, on the delta T. So we find out that the Q dot loss gain from the house is equal to 0.44 kilowatts per delta T. So it's this many kilowatts for each temperature difference between the house and the outside. So in the summertime, there's an 8-degree temperature difference. In the wintertime, there's a 28-degree temperature difference. So now let's find out what the summertime is. Let's analyze this. And in the summer, heat's going in. Summer, Q dot delta T is equal to 8 degrees. And so Q dot is equal to 8 times 0.44 is equal to 3.52 kilowatts. So in the summertime, if I have 32 degrees here, then I have to be removing 3.5 kilowatts to the reverse Carnot engine. So COPC is equal to TC over TH minus TC. And TC is 297. And the difference is 8. So this coefficient of performance is 37.12. So it's a very high coefficient of performance, but be that as it may. And then I can solve for what the power would be needed. So 37.12 is equal to 3.52 kilowatts over W dot net. So W dot net is equal to 0.095 kilowatts. About 0.1 kilowatts is what's needed in the summertime to operate the system. So that's the power that's needed going in to drive this system. Now let's look at the winter time. Here, the delta T is equal to 28 degrees. So there's a lot more heat flow that's going out that I have to replace. So Q dot is 28 times 0.44 is going to be 12.32 kilowatts. And the COPH is equal to TH over TH minus TC. So TH in the wintertime, this is minus 4 degrees C. So this is the TH and this is the TC. And now what happens is this is the Q dot out, has to go in to replace the heat that's being lost. So this TH minus TC, the 297 divided by 28 is equal to 10.6. So 10.6 is equal to 12.32 divided by W dot net, where W dot net is equal to 1.16 kilowatts. So it's a huge difference, a factor of 10 difference in the wintertime requirements versus the summertime requirements. And part of what happens when we have an ideal cycle is it gives us a very simple way to determine is this feasible or not. So what happens in colder climates is that the power requirement, even for highly efficient heat pumps, is too great and they don't function well. They function well where the outside temperatures are probably 30 degrees and above. When it gets very cold, they don't function that efficiently. So I'd like to introduce one more simple topic, and then assign homework for this area. And so now that we've had a Carnot engine that produces power and a reverse Carnot engine that consumes power, wouldn't it be nice if they got along? And so what we can do is we can have the Carnot engine, so I have the Carnot engine, it receives Qin at TH and rejects Q out. We'll make a dot on it. Q out at TC, and it's going to produce an amount of power in W dot net. So we looked at how this engine works. It receives heat, does that, blah, blah, blah. And now, what is it going to do? It could power a reverse Carnot engine. Which has heat come in, Q dot in at TC, the same W dot net, and we have a Q dot out at TH. These can be different THs and TCs, so when you have problems associated with this, and you will, pay attention to this TH and this TC can be different than these two. And so we need to pay attention to that. But the problems are not that difficult if you pay attention to what's going in and what's going out and where. So for you to have some practice with that, so for homework, 717, 729, 733, 741. And that concludes the chapter.